Empirical formulas is where we finally start to begin our journey on looking at real chemistry type stuff. Now we have to do a couple of definitions between the words empirical formulas and molecular formulas. And I'm going to show you a couple of pictures and see if you can tell the difference between an empirical formula and so I'm going to write versus a molecular formula. Okay, there's the chemical formula, which is another word for molecular formula, and there's the empirical formula. So what's the relationship? Well, if you said that the empirical formula is the reduced form, you are correct. Now, the reason that we need to find the empirical formula, well, first we have to know what it is. But then we're going to be doing some problems where we find the empirical formula so we can figure out what the molecular formula is. It's kind of like doing what Abby on NCIS does. You know, you run it through a mass spectrometer, it spits out a bunch of mass percentages, which you should have learned how to do already. And from that, we can figure out the empirical formula, and then from that, we can figure out what it really is, the real deal, the molecular formula. Now here's glucose, and this is the molecular formula, which I abbreviate as MF. Hey, no laughing. Okay, whatever. So what would the empirical formula be? Well, you're right. It's reducible by 6. So that makes CH2O. That's it. That's all there is to it. Well, that's the easy part of empirical formulas anyway. Well, that's silly. I don't know why I put that up in there. Oh, yeah, because sometimes I'm silly. So the molecular formula, determine the empirical. Okay, so this is reducible by 2, so HO. Then this one is reducible by 2, so it becomes C2H5. And this one is reducible by nothing, so this one is also the empirical formula. And this one's reducible by 2, so we end up with CH3. Excellent. Now we're ready to actually tackle the how to find an empirical formula given a whole big bunch of data. Step by step, how to. So the first thing we need to do is find the number of moles of each thing that was given to us in this compound. So here I have grams of aluminum and grams of oxygen. So pause the video and see if you can find the number of ions in each. There we go. We now have the moles of each ion in the compound. Okay, now we're ready for step number 2. So step number 2 says find the smallest molage. Yeah, that's my word, molage. That's the smallest molage. Out of the 2 that we have, that one's your smallest molage. Okay, so it's the smaller number, okay, because now I went and made it big. Divide each of the 2 molages that you got in step 1 by the smallest. So we're going to take that number and divide it by itself, so we get 1, and divide this number by the smallest molage and get 1.5. These become your subscripts to your empirical formula. These are the subscripts, and I'll say that again. This is hugely important to the empirical formula and I'm going to abbreviate empirical formula. That's it. Are you happy with that as a formula? Well, you shouldn't be. You should be kind of freaked out. You should be looking and going, dude, I didn't know you could have that 1.5 as a subscript. You can't. You can't. But you can multiply both of those by some number to get rid of the decimal. What can you multiply both of those subscripts by that would allow us to get rid of the decimal? Well, if you said 2, you are correct. So we multiply both subscripts by 2, and we end up with the empirical formula, which in this case also happens to be the same as the molecular formula. How do you know that? Well, we'll learn that later. Right now, you still just got to kind of take my word for it. But this is how the steps I just went through. Always follow these steps, and you won't get it wrong. These are always the steps to find the empirical formula. Let's try another practice problem. Now, if you think you know how to do this and you're just going to power forward and do this problem, I guarantee you're going to get it wrong because you're not going to read carefully, and that reading thing gets kids every time. So we have this much of a compound with only carbon and hydrogen, but I only gave you grammage of carbon. So what are we missing? We know that there's 1.500 grams of a compound containing those two things. I know there's 1.198 grams of carbon. You're right. We don't have the grams of hydrogen. How are you going to find that? That is correct. You subtract. So let's see. 1.5 minus 1.198. 0. I'm going to give myself a little room here. 0.302 grams of hydrogen. So what did the first step say to do? Find the molage of each one. So I'm going to take this number and divide it by 1.008. All right, so we got to convert that to moles. 1.008 grams of hydrogen, and 1 mole of hydrogen is 0.2996. And these are a good idea to take out to as many decimal places as possible. It'll make your life so much easier. Now I'm going to do the same thing for the carbon. Okay, so we're going to take that many grams and convert it to moles. So 12.01 grams for 1 mole of carbon. All right, 1.198 divided by 12.01, and we end up with 0.09975 moles of carbon. Do you remember what the next step was? Well, go back and look. Won't hurt you. Really, it won't. Okay, well, the next step then says to divide by the smallest. There's your smallest, so I'm going to divide by that number. That gives me 1. And divide this by that number. So 0.2996, well, I can't type, 0.2996 divided by that little number, we end up with 3. So these become our subscripts. So the final answer becomes C, and there's the 1, I'm not going to write the 1, H, and then 3. There's our empirical formula. Remember when we did mass percent of an element? See, no matter how much you have, the percentage of each thing does not change. For example, if you were to make a batch of cookies following the recipe exactly, it doesn't matter if you make 1 batch of cookies or you make 100 batches of cookies. If you do exactly the same recipe every time, the percentage of stuff you put in each batch of cookies doesn't change. And this is the same with a chemical formula. No matter how much of, say in this case, sucrose you have, the percentages will never, ever change. So often, if we're only given percentages, it's nice to assume we have 100 grams, because the brilliant thing with making the assumption we have 100 grams is it just makes the math easier. But you could have any grammage. For instance, if I have 100 grams of sucrose, that means then out of 100 grams, 51% of it is oxygen. 51% times 100 grams is 51. Yeah. So if you're given percentages, the rule is use 100 grams. Again, you can use any grammage, but I find it's much more difficult to pick a number like, 214 grams times 50% is more difficult to work with than 100 grams. Again, it doesn't matter how much of it that you have. The percents stay the same. So choose 100 grams. Always 100 grams. Really? 100 grams. Okay, Yes, you're going to multiply each one of these by 100 grams because in this problem we're given percents. If you multiply them each times 100 grams, that means I can ignore that and pretend it says grams because 32% of 100 is 32, which means I have grams here and grams here and grams here, but I still need to do the reading thing to make sure, because one of the common things that happens is one of these particular elements is listed, but they won't give you a percentage for it because, make your life more difficult. You got to recognize the fact that out of 100%, all of these things have to add up to 100. So what is your first step? Correct. Convert each one of these to mollages. So go ahead and pause the video and you do that and see how you do. One thing you should know about these problems is that they do fall into place beautifully. If it looks like something is not going well for this problem, chances are good you've made a mistake somewhere. These problems will fall into place very nicely. If you're not sure how to get the mollages, make sure that you ask. I'd be happy to work with you. Okay, now that we finally have the mollages, what's your next step? Well, if you said divide by the smallest, you're absolutely correct. So this one is the smallest. So I'm going to divide each one of these by the smallest, which means that this 332. So the subscript for the nitrogen then is 1. 1.332. So the subscript for the carbon then becomes 2, and for the oxygen becomes 2, and for the hydrogen we end up with, 6.6875 divided by 1.3325. So our empirical formula, and a question a lot of students I get asked by students is, how do I know which one comes first? Write them in the same order that they're given. And when all else fails, start with the carbon. That's another good rule. So we end up with C2. Then we were given hydrogen, H5, then oxygen, O2, and N. That is it. I know this problem is not on your packet, but I insist that you do this problem. You do need the practice. What is your first step? Correct. You have to find the mollage of each thing in the sample. So pause the video and see how you do finding the mollage. Please read carefully. Okay, I'm not going to go write out the how to find the moles. I assume you know how to find the moles by this point. So the moles of oxygen that you should have come up with, 1.333, was 0.0174 moles of oxygen, and you should be some of you might be freaking out because you forgot to subtract these two numbers. Notice, this is the vanadium, and this is your final mass. So the difference between the two would have given you your grams of oxygen before you can find your moles. Okay, now our moles of vanadium came out to be 0.00696 moles. All right, pause the video and see if you can finish the problem. If I divide each of these by the smallest, then the coefficient for the vanadium is 1, and the coefficient for the oxygen becomes 2.5, which is a little annoying. So what are we going to do, because we can't have points as subscripts? If you said multiply each one of these by 2, you are correct. So your final answer becomes vanadium 2O5. And bonus points for naming this guy correctly. Once again, I know this problem is not in your packet, but I do want you to give it a try. Pause the video and see if you can get through the first step and then hit play. Do not power through the entire problem, because I kind of think you might make a mistake before you get that far. So at least find the molages and see what you do, and then push play. Well, the reason I asked you not to power forward, my question is, did you get the moles of all 4 substances? Because percentages were only given for 3. But we know the maximum percentage is 100%. So if we take 100 and subtract it from the sum of all of these, blah, 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 then you're going to end up with the percentage of the one that wasn't given, which was oxygen. So you should have ended up with a percentage of 14.17% oxygen. If you need to pause and redo your molages, I understand. But I'm going to plow forward. So you should have gotten 5.2998. No, I'm not fussed about sig figs for this. Moles of carbon. Usually the more decimals the better. Not always, but usually. Then 0.8837 moles of nitrogen. And 9.722 moles of hydrogen. And 0.8856 moles of oxygen. Now these two are just about the same thing. So those, even if we divide them by this one, the smallest, that's still going to give us a subscript of 1. Then carbon, rounding to the nearest ones place, will give us a subscript of 6. Hydrogen will give us a subscript of 11, and our final formula is C6. Let's see, carbon, nitrogen should come next. N, carbon, nitrogen, then hydrogen, so H11 and O. All done. There's your homework problems to work on in class. Have a great day.